Hey, so I've got two things I want to show you really quickly before we start the Praat and Audacity lesson for the day. And the first one is I ordered a tuning fork when our class started, and it finally got here. So a little late, but I wanted to show you a couple things. So first of all, if you've never seen a tuning fork before, this is, I mean, you've seen them in the lecture, but like cartoon versions. This is kind of a small version of a tuning fork. It's smaller than what I'm used to. I've never owned one before, but we've used them in labs and things like that. So anyway, this is what it sounds like. This one's tuned to 440. If you're a musician, you know that as A. And here's the sound. You know what? That wasn't a very good hit. Whoops. So that's that pure tone that it can generate. Pretty cool, I think. But now here's something that's really cool. If you're in one of my other classes, I may have showed you this already, but this is kind of like, well, this is kind of like normal hearing. But I can also touch it to the body of the microphone, and that's kind of like bone conduction. So you can't hear it once. You cannot, ow. You can't hear this when I hold it right here. Not well. But as soon as I touch it to the body of the microphone, then you can hear it vibrate. And that's a lot like, again, bone conduction hearing. Okay, cool. So that's one thing. I was going to have that earlier, and we could take a look at how it vibrated if I slowed down the video. Okay. Second thing. I built this out of PVC pipe. Cool. And it is it's kind of a replica of your vocal tract, your nasal tract, and what we can do is so you can talk through it, and it sounds ridiculous. What you can do though is you can close one off, and you can create an anti-resonance. This is like when you're saying nasal. So in this case, you're saying a nasal. There we go. So you're saying a nasal, boo, and the sound's coming out here. This is kind of like your vocal tract, and then going up into the nasal cavity, and just coming out of the nasal cavity. What's going on right here is a closed mouth. So you're saying like an and this is like the closed mouth. So what you actually see when you investigate the waveform, which you can see behind this video, and we'll look at it in a second, is this traps, let's see. So this is exactly the length, right, from here to here, to amplify 200 hertz. And because of what we know about the mathematics is it's also going to amplify 600 hertz, right? Because we take we'll multiply it by 3, 2n minus 1, so it's going to be then 3 if we're looking for the second resonance. So that would be 600 hertz, and then the next one is 5, which would be 1,000. So this is going to amplify 200 hertz, 600 hertz, and 1,000 hertz. But this is the correct length to amplify 400 hertz, 1,200 hertz, and 2,000 hertz through this one. But what we know about nasals is, or if we know about anti-resonance, if we close off part of it, is that if I put any tone through here, but let's say, just for these purposes, that what I'm able to produce is a 200, 400, 600, 800, and 1,000, a complex tone with a fundamental of 200. Well, what's actually coming out of here is 200 amplified, 600, 400 might not. It might come out, but it'll be very not very high in amplitude because it's mostly trapped in here. Now 800 would come out, but it's not going to be amplified by this part of the tube. It's not going to be captured by this part of the tube. So you'd expect it to just be there as much as it would be if you just went, it should be the same. No amplification, no dampening. So anyway, you can kind of hear the difference between these. So here's no closures. So okay. It probably looked pretty stupid when I was doing that. But anyway, that is what's going on here. You can also hear, if you play this like a trumpet, you can hear that they have different resonances based on their lengths as well. So whoops. So you can hear that there's a different resonant frequency there. Some different timbre differences there, right? So anyway, this is another one of those, like my like this old guy. When I'm quarantined, I just build things in my garage. Anyway, all right, let's actually get to work on this Praat and Audacity stuff for the week. All right, so this is a file that's called No Sound Tube 2. It should actually be called Resonance Tube because there's still sound, but whatever. And I wanted to show you this with the nasals. So what I've done is I've loaded this file into my Audacity. I've converted it to a spectrogram, and I've put it into a Mel spectrum as well. And that's going to allow us to just kind of focus, as you know, on these lower frequencies here. So one thing that, well, let's play it really quick. All right, cool. It's like a work of art. So, one thing that I want you to look at is right here, this portion. This is when I am no tube, just, I almost said singing. That's definitely not singing, but you can see that this is the spectrogram for my voice in general, without adding my resonance tube in at all. So you can see that the major peak is right here around 600 hertz. That's the formant that you would expect for it's kind of a schwa sort of sound that I'm singing with, producing the sound with, I guess. Kind of a schwa. So you would expect that your first formant is right there. Obviously, the fundamental frequency is not right there. The fundamental frequency is a good deal lower than that. But here's when I'm using just the tube with no obstructions, this area right here. And you can see that the resonance drops. It's the same sound, but the resonance drops because I'm now blowing through this tube. So there's constriction placed on it. And it's constriction and length. So there's a tube length and there's constriction, which is pushing it way down into, I would say, the 250 range, roughly. We'll check this in a second, but it's in roughly the 250 range. Now, here's where I start cutting out. Oh, I don't want that highlight thing to go on there. So here's where I start blocking off airflow. These two right here, and you can see that things are changing. There's not a whole lot of change, but if you focus on the right areas, you'll see the change that's important. So notice this band of energy right here, and then this band of energy right here, and this band of energy up here. Now we go over here and we see there's more energy here, but where this one was, it's gone. There's energy here and it's gone here. This energy is gone here, and this energy is gone here. So they've kind of swapped places. Now, this makes sense, though, right? Because if you think about it, let me grab this guy again. So we should have resonances in this tube, this long one. So if I've blocked off the small one, we have resonances at 200 hertz, 600 hertz, 1000 hertz. And then if we go to this tube, we have resonances at 400 hertz, 1200 hertz, and 2000 hertz. Right? So they're not the same. They're all even. They're all multiples of 2. They're all going. If I was actually making a fundamental frequency close to 200 hertz, which I tried, but I don't know if I succeeded. Then there should be an actual, harmonic at each of those intervals so we could actually see it amplified if it was there. That's why I was trying to get that frequency. I'm not sure I did it. But anyway, so we should be able to see them, but we also should see them kind of oscillate back and forth, right? Because we've got 200 in this one, and then 400 here. And then we've got 600 here, but then we've got also 1000 here, and then we've got 1200 here, and then we've got another different one here, and then we go over to 2000. So you see how there's kind of this oscillatory component there, and you see that reflected in the spectrum. So now remember, one thing that we could do is we could highlight this, and we could go to Analyze, Plot Spectrum, and we can look at this. But lucky for you, I've actually already got this done. Let's take a look at these frequencies here. We've got this is our fundamental frequency, which shouldn't change for any of these. Its amplitude can change, but the actual fundamental frequency shouldn't change. It looks like I was not at all on for 200 hertz, but that's not to be expected. It looks like it's maybe around 110. Man, did not do a good job trying to get to. Well, anyway, so it's about 110 maybe. 110, and then here's our first harmonic. This looks like it's a little bit off of 200 hertz, probably at 250. Now, here's the thing. It might not be that my calculations are wrong for the tube. It might be because my fundamental frequency is off. So if I was able to sing at 200 hertz, we might actually see more accentuation at 200 hertz, but because I was off, the tube, all the tube has to work with is my frequencies that I'm producing. So if it's at about 250, so this is probably like 125, 250, 375, which that does seem about where that is. So probably I was singing at about 120, 125 hertz. So it's my fault that this doesn't look exactly right. Anyway, but what you can see is that you can see that the amplitude changes. So this is pretty cool. So notice that this is no tube at all. And like we saw, we have a formant right here. When we use the tube, but it is unblocked, the fundamental frequency has not changed in amplitude, right? If we look here, fundamental frequency is slightly above 30. We look here, fundamental frequency is slightly above 30. But the second harmonic now becomes the first formant. It's jumped way up. It's become accentuated. So it's got power that wasn't there without the tube. It's actually being amplified. And the harmonic that was the first formant, it looks like it was about here. Nope, it was this one. This has been dampened. Okay, so now let's compare these two. So we have the long tube blocked, and this should be a reduction in the 200 hertz range because the long tube is blocked. So we're creating an anti-resonance in the long tube, and so it should soak up some energy at 200 hertz, 600 hertz, and 1,000. And what we see is that does look like it's happening. We've got less energy near 200 hertz. So again, this is about 250 because it's the harmonic that it had to deal with. But it has less energy at 200 hertz than it did in either of the other. Remember, in this one, the 250 close to 200 hertz was very accentuated. Here, it was higher than the fundamental, but here, it's a lot lower than the fundamental. The one close to 400, about 375, this should be amplified because our short tube is not blocked, and that's exactly true. It's amplified beyond where it is in either of the other cases. When we look at the short tube being blocked, now we've got the 200 hertz tone coming through a bit better. Not as good as it did in the tube unblocked, but we do see that it's higher than it was with the long tube blocked. And then we also see a change for the 400 hertz frequency. It's now amplitude is very small compared to its height over here. So we can see that we're setting up resonances and anti-resonances just by blocking off those tubes, which is exactly what's going on in your mouth when you're saying different nasal sounds. All right, so this file's up. If you want to follow along and look at that, you can and should. Your task is twofold because we're actually putting together 2 modules worth of work in this one because they're all semi-vowels and consonants that we're working with this time. One thing that I want you to do is go into Praat, Go into Praat, and I want you to look at 2 different words that I have for you. One is going to be a word without a nasal, and one is going to be a word with a nasal. I want you to compare the vowel to the nasal. What I want you to look at is bandwidth. So in Praat, remember how to get bandwidth. So select a portion, and you're going to go to formant, and I want you to look at the bandwidth of the formants. Which one, before you do it, which one should be larger? Think about that. And then when you look at it, which one is larger? All right, so this is that kind of like aphasia word salad gobbledygook that I posted for you guys. And what you've got, this is what it sounds like.
Old propriety.
So old is the first word. So this is great because what we've got is we've got a vowel, we've got a semi-vowel, and then we've got a consonant. And so you can look at this portion right here. This should be O. Yeah. And then we should have an L, O. It's still a little bit of O in there, but it's a semi-vowel, right? So it's a little hard to tell the boundary between the vowel and the semi-vowel. But what you can see, if you look at the formants, is that you can see formant 1 right here. This is the fundamental frequency. But you can see formant 1 rising up for this semi-vowel. You can see formant 3 dropping for the semi-vowel. Formant 2 is remaining pretty constant. And then, I was going to say consonant. And then what you've got right here is you've got the D. Duh. Which I didn't pronounce fully, apparently. The whole word sounds like this.
Old.
So that's the D. Old. It's kind of a weird D. You can see that it's weird if you look at it too, because it doesn't have exactly the right unvoicing, right? There's not as much of a drop in voicing as you expect for, say, right here before the P, before propriety.
Propriety.
But it's sort of there. And then you can also see that there's not the amplitude isn't as great for the release on the D either. Not like, again, the propriety over here. So it's a little bit of a weird, kind of a weird D. The O and the L are about like what you expect.
Old.
And then the P here looks just like we would expect a plosive to look like. So we have this unvoiced portion right here, right there. And then this is our voiced onset time right here. See, no sound. And then we've got, starting here,
Propriety.
the P. And you can see that there's a little bit of a lag between the P and the beginning of the next consonant, the R. Then we have our R, which again is a semivowel. So it should be transitioning again, which you can see in these formants here. Again, formant, this looks like 2, is coming up a little bit, very curvy right there. It's kind of really curvy formant 2. But you can see it moving up to meet the pr, which I think is how I pronounce the propriety. Propriety. Like there. And then we have another P. And you can see that these P's look a lot alike. And then another R. But now these R's are going to look a little different. There's similarities. They start in about the same place, and they're changing with each other, like each other. But this one goes to a pr, so this goes into and this goes into I. So you should see, which we do, that here the going into pr, this formant, that's interesting. Format 1 should be dropping a little over here, and it's not. That's kind of strange. But anyway, you can look at format 2 here. It doesn't rise as much. It shouldn't, right? Format 1 and 2 for the are very close together, and then for I, they're a little bit further apart. So you can see here that format 2 is rising a bit more, which it should be. But they start in approximately the same place. So we've got these R's. But remember, they're semivowels, so they're transitioning into the vowel. So what does the rest of this sound like?
Propriety.
Okay, so here's our R. And you can see that that sounds a little bit different than this. Right, so maybe we're catching a little bit of the vowel, but you can still hear how, even though they're both R's, they are changing. They're moving with the vowel that's after it. I. So this is kind of a diphthong here. So we're going from I to e. I. You can see that right here. So there's some motion here. This flattens out a little bit. Format 2 drops a little bit, and then format 3 looks like it. I can't really visualize that one very well because it looks like format 3 melds with format 2 here, or possibly it continues on. Just visually, I can't tell. And then this should be our T, which sounds like D. All right, so then we go D. Again, not a great stop consonant here, but you can see that there is some an unvoiced portion right here. And then we go to our... Nope, that wasn't enough. into the D and then E. And because this is an E, you notice that format 2 is very high, right? In fact, we might not even be able to see the first format there. Let's see what Praat has to say. Yeah, okay. So I would agree with that. This one drops down enough that it looks like it's probably on par about with the fundamental frequency. We can look at that if we go to pitch and show pitch. Yeah, so it thinks that fundamental frequency is pretty much on par in the same sort of location as the first format. It's probably not. We know that the fundamental frequency should be lower than the first format. I think what's going on here is our range. Like we're going from 0 to 5,000. So I think we're kind of conflating the two just because they're so close together. If we zoomed in, we'd probably see some difference there. But anyway, we have this E phoneme, which we know has a very low first formant and a very high second formant. You can see that for the entire sentence, these are the two most distant format frequencies. And you can see the drop like that. And then here we've got this glide that comes up and then flattens out a little bit here. So we should be able to look just right here for the second half of our diphthong. Yeah. And this should be our I. All right. So this brings me to your task, your second task, your task that involves the module that you just completed. We're kind of to the portion of the class where I've taught you how to use Praat to look at where the formats are, right? You know what to do. You know that you can, you know that we can pull off part of this semi-vowel here. It doesn't really make sense to pull formats from a semi-vowel though, right? Because it's going to average them. To get the first format, it's taking the average for the selection. So I get 664. If I play this, if we take maybe just the first half, 499, or about 500. And if we take the second half, $698, about 700. So it jumps by about 200 hertz for that first format, which we would expect because, again, it's a semi-vowel. It's transitioning into the vowel that follows it. So, I mean, does it make a lot of sense to find the formats there like we were with our vowels? Not so much. You can. I mean, you can do it just to give yourself a better idea that that format is rising, except that we've got the speckle on the screen here. And we've got the speckle on the screen. You don't really need to measure it. So we're at the portion where now we know that we can measure vowels. What we have to do is we have to visually identify our semi-vowels. And we also have to pretty much visually identify our consonants, our stop consonants, and nasals as well. So, like I was saying, your second task is I'm going to give you a waveform, a completely unidentified waveform. And I want you to tell me what you think it says. Remember, these Praat and Audacity portions, these are for extra credit. And the other thing is I'm going to be pretty lenient on this as well, because I understand that when you're looking at, so we know that a s and a sh look different than one another. In fact, let's just do that really quickly. S, sh, sh. All right. So we see a difference. Let's zoom in really quickly. There we go. That's pretty good. We can see a difference in these when they're both there to compare, right? So we've got a s, which is right here. There's a lot more high frequency, as we would expect. And then we've got a sh, which has a lot more low frequency, which also we would expect from a s and a sh. Again, we can play these. S, sh. So a s has a lot of a high frequency component, a sh has more of a low frequency component. And then when you do the two together, you can actually watch them glide from one to another. So we have this high frequency component which gets really muddled over here and not very good. And then we've got this, which you can see drop. This one's there, this goes away entirely. So you can see lots of amplitude up here and then much more amplitude down here. Not a whole lot of amplitude here, and then it becomes apparent here. So even though they're broadband, we do see that there are characteristic energies. But here's the thing. It's one speaker, it's me, and you have something to compare it to. If you saw these in isolation and they were from different speakers, you would probably know that these are noisy vowels, right? Some sort of fricative. But would you be able to tell the difference between a s and a sh without seeing the two? So if you said that it was, sit, and well, no, it's a bad example. So if let's say it was sun, you thought it was sun, but it was actually shun. I wouldn't count off for that because you don't have anything to compare it to. Now, if I gave you two, and I said one of these is sun, one of these is shun, and another one is chun. It's not a word. Sunk, shunk, and chunk. Chunk isn't a word. I'll have to do some work to try to figure out words that have all those same phonemes in them. Anyway, then I would expect you to get the right answer because you have something to compare it to. You'd be able to say what is a s and a sh when you see them together. But when I give you a word in isolation, again, if you say shun and it was sun, I'll count that as correct because you're using the right kind of vowel. So that's acceptable. Maybe also if you said some and it was actually shun, I would accept that as well because you know that it's a nasal. You're identifying a nasal correctly. But again, you don't have the and the n to compare it to. Let's again, really quickly, take a look at the difference between those two. Some, sun, some, sun. If we want to look at our plot like Audacity, when we plot the spectrum, we can come up to Spectrum and say View Spectral Slice. This is once we have something highlighted. You're going to need to zoom in, move over. You can kind of see why I like Audacity's version of this better. Also, it's prettier. All right, so here we go. So this is our spectrum. We're looking from 0 to about 1400. And you can see that this is likely our anti-resonance right here. Or it could be here. But this is So it should be a low anti-resonance. What we would expect in the N, is we would expect it to move a little bit back, which we'd expect to shrink the cavity, which we'd expect to create a higher frequency. So let's take a look at that really quickly. Okay, so now we're zoomed in as much as we were with the M, and you can see that that anti-resonance that we saw right here is not there anymore. Neither is it here. It looks like it's possibly moved to right here. If you click, it'll give you the frequency where you are, 572. So maybe it's 572, maybe it's 1163. Those are harmonics of one another, so, or they're close anyway. So it's probably this one, 572. That's probably your anti-resonance for the Okay, so let me get rid of this. Let's look at our M again. There we go. Spectrum, view that slice. And 2, 3, 4. Yeah. Looks like it's right there for the M. 189. Maybe right here. 424. So you can see my money's on that 189, 192 area. So that looks like where the anti-resonance is for the M. And then you could see it differently for the N. So your third task is, I want you to find the anti-resonances for some words that I give you, for some nasals that are in some words. So you'll find the instructions for all those on Canvas, and good luck.